In the last lecture, I gave an overview of how the atoms that are now inside you and me were originally made inside stars that lived and died several billion years ago. It's a wonderful story, and one of its qualities is that it connects us directly to the wider universe. But you also may have noticed that I just told you the story. I didn't really include much evidence for it. How do we know that's what actually happened? Well, I hope by the end of this lecture, you won't have any lingering doubts. See, our approach is going to be to focus on the relative abundances of the various chemical elements. For example, the fact that iron is common and that gold is rare. So we're going to need to look at how element abundances are measured out in the galaxy. Then we'll look at the theory of nucleosynthesis to see what it predicts for these abundances. And then finally, it's the stunning match between theory and observation that makes this subject one of the great triumphs of 20th century science. So let's begin by seeing how astronomers figure out what stars are made of. It seems quite amazing that just by looking at a star, you can actually tell what it's made of, but it turns out you can. Remember from lecture 4, when a hot gas glows, its atoms give off light with a specific set of colours. Here are some examples. Each element glows with its own set of colours. It's a kind of barcode that acts like a spectral signature, a different barcode for each kind of atom. Now, in these examples, the colours are seen as bright or emission lines, but in other circumstances, the atoms can absorb these same colours and the barcode appears as dark absorption lines against the bright white light continuous spectrum. Here, for example, is the full spectrum of the sun, which shows the strongest lines. But a more detailed spectrum shows hundreds of lines. The barcodes from all the different elements are superposed. So obviously, by identifying the various barcodes in these spectra, you know what elements are in the star. Now, as it happens, measuring the relative amount of each element, the element's abundance, is much more difficult. And it wasn't until 1925 that a young British-born PhD student at Harvard Observatory, Cecilia Payne, finally developed a method to do this. And using this method, she was the first person to realise that the stars were primarily made of hydrogen and helium, and not iron, as had been previously thought. Now, in the 80 or so years since that time, the science of measuring cosmic abundances has become really quite mature, and we now have a very good idea of the composition of most of the objects in the universe, whether they're like the stars here or gas clouds like these. So what do we find for the cosmic abundances? You can actually boil the results down to 3 primary conclusions. First, almost always one finds about 3/4 of hydrogen and 1/4 of helium, and a small amount of all the other elements, somewhere between 0 and 4%. Without doubt, the primary elements in the universe are hydrogen and helium, while all the other elements are an afterthought. Now, this result might puzzle you a bit, because obviously the Earth certainly isn't made mostly of hydrogen and helium. But the Earth is an exception. Its gravity is too weak to hold on to these 2 light gases. So it lost them long ago, and it's made almost entirely from the other element category. Okay, the second result is that the overall fraction of heavy elements, that 0 to 4%, varies from object to object in a very interesting and systematic way that we'll look at in the next lecture. But the third result is that the relative abundances within the heavy elements are very similar in all objects. And this is going to be one of our key themes for this lecture. So let's look at these relative abundances now. Remember, the most common way to see all the elements is arrayed in the famous periodic table, all 92 of them. But to astronomers and physicists, this graph of their relative abundance is much more interesting. So the x-axis runs along the element series from hydrogen to uranium, and the y-axis shows the relative amount or abundance of each element. Now notice the y-axis is exponential and spans a huge range. For example, for every 10 billion atoms of hydrogen, we have 1 million atoms of silicon, 100 atoms of zinc, and just 1 atom of lead. Now, its overall shape has a steady decline with a number of peaks along the way. Hydrogen and helium are by far the most abundant elements. Then there's a precipitous factor of 1 billion drop to the light elements, lithium, beryllium, and boron, that are extremely rare. Then comes what is called the alpha peak, with familiar elements such as carbon, oxygen, neon, and magnesium. Then another dip before a major peak, the iron peak, in which iron and nickel really stand out. From then on, it's a gradual decline to extremely rare elements. But superimposed on this declining slope are 3 pairs of smaller peaks, which, for reasons we'll get to, I've labelled R and S. Now, overall, this should jive with your own knowledge of the elements. You've heard of the common ones, oxygen, carbon, silicon, iron, because they're common, while the rare ones we've often never heard of, niobium, molybdenum, dysprosium. And the few times you have heard of them, gold, silver, platinum, is precisely because they're rare. I mean, that's why they're valuable. But remember what I mentioned a minute ago? This abundance curve is found wherever you look. Stars, planets, interstellar gas, it's always the same. This is a wonderful example of our world mirroring the cosmic world. See, gold isn't just rare here on Earth, it's rare everywhere. And carbon and oxygen aren't just common on Earth, they're common everywhere. Now, having introduced the abundance curve, we're going to spend the rest of this lecture trying to understand its shape. The overall framework, of course, we met last lecture. Thermonuclear fusion reactions deep inside stars make these elements. But there's much more to the story than I gave you, and it's remarkable how all those peaks can be explained by the properties of atomic nuclei and the properties of star furnaces. So let's start with the first step along a long road to heavier elements, from hydrogen to helium. Now, last lecture, I said that protons simply collide and stick. But in truth, this is an exceedingly difficult reaction for protons to achieve, because the reaction doesn't involve the strong nuclear Velcro force, but instead the weak force of radioactivity. And this makes the reaction extremely unlikely. Here's the actual reaction. 2 protons react to make deuterium, a heavy version of hydrogen with 1 neutron, and an anti-electron and a neutrino are ejected. This reaction is so rare that in the core of the Sun, it takes the average proton 1 billion years to react, despite its colliding with another proton 1 billion times every second. So the Sun's furnace burns its hydrogen fuel incredibly slowly. A cubic foot of your digestion is 400 times more powerful than a cubic foot of the Sun's furnace. It's an extremely gentle furnace. The Sun is so powerful only because its furnace is so big. As you might imagine, it's because the hydrogen fuel is consumed so slowly that the Sun and stars have very long lives. In the case of the Sun, nearly 10 billion years. And this slowness of star lives has a crucial cosmological significance. If stars evolved much faster, galaxies would have gone dark long ago, and there'd be no time for life to evolve. Okay, back to our reactions. Once deuterium is formed, things proceed more rapidly. Deuterium absorbs another proton to make helium-3, a version of helium with only one neutron. Then two of these collide to make normal helium-4. Overall, these reactions have effectively combined 4 protons into a helium nucleus, and that's the nuclear ash from this first hydrogen fuel. So far so good, but what about the next stage? How do we go beyond helium? It turns out that this is also extremely difficult for the simple reason that the two obvious next steps are blocked. Now, to help see this, I want to introduce an exceedingly useful kind of diagram that places all nuclei on an XY plane. Up the y-axis, we have the sequence of elements, defined by the number of protons. And along the x-axis, we have the number of neutrons. So every nucleus can be placed on this graph. The unstable ones I've coloured purple. Now you'll notice that each element has several possible nuclei. For example, lithium, with 3 protons, has 2 versions, or isotopes, to use the proper word. Lithium-6 with 3 neutrons, and lithium-7 with 4 neutrons. Notice the number in the name refers to the total number of protons and neutrons. Now let's see what options we have for helium-4. Well, adding a proton would shift it up one place, to lithium-5. But that nucleus doesn't exist, so that reaction isn't possible. What about colliding 2 helium-4 nuclei together? That would move 2 spaces up and 2 spaces to the right, landing on beryllium-8. But this is an exceedingly unstable nucleus. It lives for just 10 to the minus 16 seconds before breaking apart back into 2 helium-4 nuclei. So that reaction is also blocked. Now, what actually happens is rather remarkable and was first figured out by Ed Salpeter and Fred Hoyle in the early 1950s. Nothing can happen until the helium core of a star crushes down to reach a density of many kilograms per cubic centimetre and almost 100 million degrees. Only then is it possible for 3 helium nuclei to collide almost simultaneously to make carbon-12 in what's called the triple alpha reaction, because another name for a helium nucleus is an alpha particle. In effect, the first 2 helium nuclei collide to make beryllium-8, but before it has a chance to break apart, a third one comes zooming in to make carbon. Well, we're making rather slow progress up the periodic table. We've got as far as element number 6, carbon. But things go a little faster from now on. In fact, historically, everything fell into place in 1957 with a landmark paper by this group of 4, Margaret and Jeff Burbidge, Willie Fowler and Fred Hoyle. And their paper is now viewed as a classic and is often referred to simply as B²FH from their initials. Now, in addition to hydrogen fusion and the triple alpha reactions, they spelled out a number of other nuclear pathways that generated essentially all the other elements up to and beyond uranium. So much of the story I'm about to tell you has its roots back in their paper. So let's return to a larger version of our graph of possible nuclei. You can see down on the lower left, we've already gone from hydrogen to helium via deuterium at 10 million degrees. Then the triple alpha reaction takes us from helium to carbon-12 at 100 million degrees. And at that point, the reactions get a little easier. You see, the helium nucleus, the alpha particle, is such a robust little entity that it keeps getting added to nuclei to make a sequence called, not surprisingly, the alpha elements. See here, we jump by 2 protons and 2 neutrons from carbon-12 to oxygen-16 to neon-20 to magnesium-24, to silicon-28, and to sulfur-32. All these elements are quite abundant. Back to our abundance graph, let's zoom in on this alpha peak. The alpha elements are the red dots. You can see they have abundances typically between 10 and 100 times higher than the elements in between. Things like fluorine, sodium, aluminum, phosphorus, chlorine, and potassium. Now you might wonder how to get these elements in between. Well, at even higher temperatures, more like 1 billion degrees, then other reactions occur. For example, carbon-carbon or oxygen-oxygen fusion creates a much wider range of elements. Now remember the reason these reactions need higher temperature. The nuclei have more protons, and so you need higher temperature to overcome their much stronger repulsion. Now these conditions are getting pretty drastic, so let's see where all this is heading. Remember the all-important binding energy curve from last lecture. It shows the glue energy stored in the nucleus. As long as a reaction moves downwards, then energy is released and a star can still shine. But you can see the problem here. The fusion reactions yield less and less energy as they move down towards the bottom of the curve. And ultimately, when they get to iron, element number 26, that's it, game over, no more energy is available. Iron nuclei are the ultimate ash from fusion reactions. So without going into details, I think you can see how fusion reactions tend to generate large quantities of the elements around iron. And sure enough, this is exactly what's found. Let's go back to our abundance graph. The iron peak stands out from elements 24 through 28, chromium, manganese, iron, cobalt, and nickel. They're all cosmically quite abundant, with iron significantly more than the others. Okay, this is great. I mean, we've managed to make elements up to the iron peak. But at this point, our path is blocked. Normal fusion can't generate heavier elements, and we need a radically different mechanism. Now, this is where neutrons enter our story in a big way. I mean, in a sense, they come to our rescue. So let's see how they do this. Here's yet another part of our neutron-proton graph. We're further along the sequence here, with iron 56 at the lower left. It has 26 protons and 30 neutrons. Iron 56 is called a seed nucleus. Now, in certain stars, some reactions make free neutrons, and because they have no charge, they can sneak into any nucleus quite easily. So let's add a neutron to our iron 56 seed nucleus. We make iron 57. Add another, we make iron 58, and add one more to make iron 59. Now, iron 59 is unstable, and one of its neutrons changes into a proton by spitting out an electron. Bingo! We move up and to the left to make cobalt 59, a new element. The process continues. Adding a neutron to cobalt 59 makes cobalt 60, which in turn decays to nickel 60. So do you see what's going on? By steadily adding neutrons, we can sneak up the sequence following this zigzag path, making unstable nuclei, which then decay by neutron conversion into protons. Now, as we move up this path, a fascinating thing occurs. When we get to 50 neutrons, the elements begin to build up. Basically, they don't like to absorb another neutron. And when they do, they quickly decay back to the next element up, keeping the number of neutrons at 50. Now, why do nuclei like to have 50 neutrons and not 49 or 51? Well, the answer is really quite delightful. You see, the protons and neutrons aren't just sort of glued together like the red and blue spheres in my diagrams. They're actually on orbits within the nucleus. And just like electrons orbiting within atoms, they orbit within shells. Now, you may remember from high school chemistry that when electrons fill a shell in an atom, that atom is one of the noble gases, things like helium or neon or krypton, on the far right of the periodic table. These atoms are particularly stable because their electron shells are filled. Well, exactly the same kind of pattern happens inside atomic nuclei. Protons and neutrons orbit within shells, and when a shell is filled, that nucleus is especially stable. The particular numbers when this happens are called magic numbers, and the nuclei are called magic nuclei. So now let's step back and look at our entire neutron-proton diagram, from hydrogen all the way up to and beyond uranium. In black, you can see all the stable nuclei. They curve over to the right because, remember, stable nuclei tend to have more neutrons than protons. Now, either side of the stable black nuclei are unstable nuclei. To the right are neutron-rich nuclei that decay by spitting out electrons, moving back to the stable nuclei. In fact, you can understand why physicists call this the nuclear valley of stability. The stable nuclei lie along the valley floor, and the walls of the valley rise on either side. And naturally, nuclei tend to roll down the walls back to the valley floor. Now here are the magic numbers. They're at 2, 8, 20, 28, 50, 82, and 126. Nuclei with this number of neutrons or protons are particularly stable and robust. They're the nuclear equivalent of the noble gas atoms. So now let's look again at our neutron pathway. Up it comes, and where it meets these magic numbers, the elements build up, here near zirconium, barium, and lead. But wait a minute, let's go back to our abundance diagram. That's exactly where we have peaks on the abundance plot. Here they are, at just the right location. You'll notice I've labelled them S process to distinguish them from the other 3 peaks that are close by called R process peaks. Why are there 2 sets of peaks? The answer is it's all to do with what frequency the neutrons are added. S stands for slow and R stands for rapid. See, here's our close-up of the S process path. Here's the line or valley of stability. Now, just a little way from that line, the nuclei are only mildly unstable, and it takes sort of days to years for them to decay. So as long as the neutrons only get absorbed infrequently, say 1 every 1,000 years, then each new nucleus has time to decay. That's what defines this particular path, the S process path. Now, let's consider this region further away from the valley of stability, up the valley walls a bit. The nuclei are now much more unstable. They take only fractions of a second to decay. So now imagine our seed nucleus was subject to a very rapid bombardment of neutrons, getting smacked many times per second. This time, the neutrons would pile in and push the iron into a very neutron-rich location, perhaps iron 66, before it would decay. So the path with rapid neutron addition would be more like this green line. Let's back out to see the larger picture again. Here's the calculated path for an iron seed nucleus in a billion-degree neutron gas of roughly water density. You can see how the path stays far to the right of the stable nuclei, and the nucleus makes rapid progress, passing the magic numbers at 1/10 1/2 and 2 seconds, and even reaching such heavy nuclei that fission breaks the nucleus apart and cycles it back round. Notice how, just like the S process pathway, the R process accumulates many nuclei around the 3 magic neutron numbers, 50, 82, and 126. Now, if the neutron flux shuts off, all those nuclei decay. They roll back down to the valley floor from the valley wall. Neutrons converting into protons by spitting out electrons. They move diagonally to the left and up. So those regions of excess at the magic numbers end up here, as excesses near the elements selenium-80, tellurium-130, platinum-192, and even up at thorium and uranium. As you can already guess, these correspond perfectly to the second set of abundance peaks on the abundance graph. Here are the R process peaks, offset slightly from the S process peaks. Now, so far I've only referred to the S and R processes. Where might we find the right conditions for these mechanisms? Well, the slow path is thought to occur in very luminous red giant stars, where certain reactions make free neutrons. Over thousands of years, these neutrons get absorbed by heavier nuclei and populate the slow S-process pathway. In fact, we know this happens because the spectra of these stars show enhanced S-process elements, including the smoking gun element number 43, technetium. Now, this element has no stable nuclei. It decays within 1 million years, so it must have been made recently before getting dredged up onto the surface where it leaves its mark in the spectrum. Now, the site of the R process, the rapid addition of neutrons, is thought to be core collapse supernovae. I don't have time to go into details, but as the core collapses, it forms a neutron star. So for a few seconds, there is a Herculean population of neutrons coming out of the core and into all the surrounding matter. It's a huge population of neutrons that drives the nuclei up the neutron-rich R process pathway. A few seconds later, when the explosion is over, the nuclei then start decaying back to the line of stability. Now, at this point, all I've done is to show you a few of the mechanisms that generate the various features on the abundance graph. The production of helium and carbon, the alpha and ion peaks, and the S and R processes. Now, in truth, this subject is much more advanced than I've portrayed it. The lives of all the types of stars are calculated, including all the nuclear reactions that fuel their furnaces. The dredge up and ejection of the elements are folded in, and the slow multi-generational build-up of elements in the galaxy is modelled. And of course, the observations of abundances in all kinds of locations gets ever more refined. The bottom line is that there is a stunningly good match between the calculated and the observed element abundances. Let's not forget, there are over 200 abundance values, one for each isotope, and these values range over a factor of 1,000 billion. The calculations get essentially all of them correct to better than a factor of 2. This is amazingly good and should convince you that we really do understand the origin of the elements. And from any perspective, this is one of the great achievements of 20th century science. But of course, it's more than a scientific success story. It's a fundamental part of the cosmological account of how we came to be here. Perhaps more than any other of the lectures in this course, this one forges the closest link between you and the universe. You now know enough to trace the story of most of the matter that's around you back to its origins. Within my hand, for example, the iron that makes the blood red Those atoms were most likely born in a white dwarf supernova. The carbon atoms that make up my fingernails were born in a sun-type star. And the gold in my wedding ring, it sits right next to platinum on the R-process peak. These atoms have actually experienced the billion-degree chaos of a massive star's core collapse. They know what it is to be hurled at 10th light speed out into space. All of these atoms have witnessed the deep cold between the stars. They're all older than the Earth, and they'll all outlive the sun. If you ever feel weighed down by the banality of life, take a look at your surroundings. Take a look at yourself and try to feel the cosmic in the local.